Welcome back, students, and thank you for once again visiting my YouTube channel, HansenMath. In today's video, we're going to look at composition of functions and inverse functions and some of the interplay between them. So without further delay, let's get right to it. Okay, here you see that it says find f of g of x. So that symbol there means you're doing a composition of functions. You're going to plug g into the f function. And we're also going to find g of f of x. And then finally, we're going to find f of g of 3. So I will go over all three of these scenarios with you in fine detail. So what I'm going to do first is I'm going to kind of divide my screen up here like so. And first, we're going to work on this case right here, which is f of g of x. So I'm going to write it in an alternative way. We're starting with the f function, that's the outer function, and we're doing f of g of x. Okay, so f is the outer function, we're going to be plugging in g. So since f is the outside function, what I like to do and what students have liked is I write out the outside f function verbatim, which is x squared minus 2x. And then, since we're going to be plugging in the g function right here, I'm going to get ready. So x is our input. So I'm going to, instead of writing down x, I'm going to put an empty parenthesis for x. So instead of x, we have empty parenthesis squared minus 2. And instead of this x, I'm going to put another empty parenthesis because we're going to substitute in for x from the f function. Okay, so again, instead of x squared, I have parentheses squared, and instead of minus 2x, I have minus 2 empty parentheses. So quite literally, we are going to plug into the parentheses the entire g of x function, which, as you can see up here, is, or over here rather, 5x plus 1. So 5x plus 1 goes into both sets of parentheses. Okay? So now we'll do a little bit of organizing here. We've got 5x plus 1 squared. So that means that we have 5x plus 1 times itself. Okay, that's how you square the binomial there. And then we have, I like to think of this as a negative 2. This negative 2 distributes to the 5x and to the 1. So negative 2 times 5x is a negative 10x, and negative 2 times positive 1 is a negative or a minus 2. Okay? So now we have to FOIL out these this multiplication of binomials. So we got first, 5x times 5x is 25x squared. Outermost would be 5x times 1. And innermost is 5x times 1. So that's 5x and another 5x, which would be 10x. And then the last term of each binomial to multiply for the FOIL, 1 times 1 is 1. And then I'm going to recopy my minus 10x and then my minus 2. Now let's try to combine like terms. The only thing that we have x squared is just this 25x squared. So I'm going to write down 25x squared. Let's see, we have a plus 10x, and then down yonder we have a minus 10x, those offset. And then we have a plus 1 and a minus 2. 1 minus 2 is negative 1. So that is the result here of taking f and plugging in g of x. Okay? So let's see what happens when we reverse things around, and instead of f of g of x, right now, let's try to do, let me switch colors. Let's do g of f of x. So now g is going to be the outer function, and we're going to plug in f of x. Okay, so since in this case, since g is the outer function, I'm going to write out the g function exactly. All right, so let me get back to my pen. So since g comes first, I call it the outer function. We're going to write that down, which is literally 5x plus 1 from right here. So 5x plus 1. And now I'm going to rewrite that, but instead of 5x, I'm going to do 5 times an empty parenthesis because we're about to substitute in for x. And then the plus 1 comes at the end. Now, what are we substituting in for x? We're substituting in the f of x function. That's what's getting plugged in here, as you can see in parentheses. So if we look, what was our f of x function? It was x squared minus 2x. So x squared minus 2x goes into our parentheses. So now there's nothing to it but to do it. We have to distribute this 5. So we have 5 times x squared is 5x squared minus 5 times 2x is 10x. And then bring down your plus 1. Let's see, all these terms are different. So we are all good. That is g of, make that a little bit neater. That is g of f of x, which you may write like that, or you can write it like this. Okay? So finally, now that we've got f of g of x and g of f of x, there was one more task here. If you go back to the top, it says we have f of g of 3. Okay, so let's go back to our f of g, which was this one, and now it says evaluate it at 3. So that means you plug in 3 for x. So let's go right back here, and we've got 25x squared minus 1. So now all we're going to do is we're going to write f of g of 3, which means that we take this equation and we plug in 3 for x. So instead of x, it becomes 3. We still have squared minus 1. So we have 25 times 3 squared is 9 minus 1. So we have 25 times 9. 25 times 9 is 225 minus 1 is 224. So when you plug in a specific value, you will get out an answer, okay? You'll get out an output or a numeric answer. So there is a little crash course in doing a composition of functions. We did f of g of x and then g of f of x, and then we also plugged in a specific value. So we're going to do 3 examples here. This was example 1. Example 2 will be similar, and then we have a third example which kind of ties everything together. So keep on trucking, and let's look at one more example like this. Okay, in our second example, again, we're going to look at a composition. Let's do f of g of x and g of f of x. So again, if you would allow me to kind of draw a line down my screen so we can do both. So let's start with this one first, f of g of x. So I'm going to rewrite it like f of g of x. Okay, so notice that my outer function is f, so I'm going to write the f function down verbatim, 2x cubed plus 1. And then I'm going to rewrite it, but instead of x, I'm going to use an open parenthesis. Sometimes I call it a shell because we're leaving space for replacing x or substituting into x. Okay, I can't forget to write down my plus 1 from the end of the function. And now, what are we going to plug into this function? We're plugging in the g of x function, the entirety of it. So if you look over here for the g of x function, it is the cubed root or third root of x minus 1 over 2. All right, so that's the substitution step. So now let's look at simplifying. So we've got equals, we've got 2 times, let's see, we got the cube root of x minus 1 over 2 cubed. When your index matches your power, they cancel out, okay? So the cubed root's gone, the third power is gone, so you're left with just x minus 1 over 2, and then the plus 1 at the end will bring down. So now, since we're multiplying by 2 and dividing 2 out, those cancel. So we have x minus 1 plus 1, bringing that down. So x minus 1 plus 1, the minus 1 plus 1 cancels, so we're left with just x. Okay, so f of g of x is just equal to x. Huh, that's rather concise. Well, that is f of g of x. Now let's flip it around and let's do the second case here, g of f of x. So I'm going to write that out. G of f of x is equal to, now since g is the first or the outer function, I'm going to write down the g function exactly as I see it, which is right here, which is the cube root of x minus 1 over 2. Okay, I'm going to recopy it again, and I'm going to do my little shell gimmick where instead of x, I leave an empty parenthesis shell. Okay, then I still have my minus 1, and I still have everything divided by 2. So now, we're taking x, we're replacing it with this empty parentheses, and what are we plugging in? We're plugging in f of x, which is the inner function. So f of x was our 2x cubed plus 1. So 2x cubed plus 1 goes in. So now we have to do some simplifying. So we have the cubed root of, now you got to do everything inside this cube root first. So we've got 2x cubed plus 1 minus 1. The plus 1 minus 1 canceled, they offset to 0. So we have 2x cubed over 2. So now we have 2 on top, 2 on the bottom. Those divide out. So now we have the cube root of x cubed. And similarly, like we saw earlier, when you have the third root and the third power, those offset. So we're just left with plain old x. Huh. So now this is very interesting. We did f plug in g and we got out x. And then we did g plug in f and we also got out x. So you got to wonder yourself, is there something bubbling just beneath the surface, or is this a grand coincidence? Well, what we're going to do is we're going to take a look at this graphically and see what's going on. So now I'm going to hit pause and I'm going to flip over to Desmos and show you guys what this looks like from a graphical perspective. But before we go on to Desmos, take a look. My slide inadvertently changed and I couldn't see it. We are still on the same problem of finding f of x and g of x when f of x equals 2x cubed plus 1 and g of x equals the cube root of x minus 1 over 2. So those will be the problems that we are putting into Desmos right now. All right, so now we are over on Desmos, and you'll see right now in red, you're looking at our f of x function, which was 2x cubed plus 1. And then now I will hit with my mouse also the g of x function, which is the cube root of x minus 1 over 2. And notice that there's something going on here. And what if I look at a particular coordinate? What if I look at this one here? This is 2, 0.794. And then if I go out to here, 0.794, I'm going to get really close to 2. Or maybe if I go over to 6, I'm at about 1.357. And if I go on the red graph to 1.357, I'm at about 6. So what's going on with the coordinates of these two graphs? Well, what happened is the following. Remember when we did f of g of x and g of f of x on the previous slide, we had x for both of them. So what you've actually found there is you found the identity function. So if I plug in y equals x, you'll see that that cuts, that's a straight line with a slope of 1 cutting through the origin, and that is a mirror line or a line of symmetry or reflection. It cuts this picture in half, and if you were to fold or flip the red line, it would go exactly onto the blue line or vice versa. So this is a line of symmetry or a mirror line or a reflection line. So if you have inverse functions, the picture will always look like this, where it'll be a mirror image across the y equals x line. This is one way that you can prove that you have indeed found a pair of inverse functions. And again, the domain and range are completely reversed. So for example, on this g of x function in blue, if I find the point 8 comma 1.518, over here, if I find 1.518, I'll be at 8 as my output, okay? So as I'm trying to show you guys, the input and output are completely reversed. So like, for example, like right here, if this was really close to like 18 comma 2, on this one, I'd have to have 2 comma 18, like so, okay? So your x's and y's are completely reversed. All right, so that is a graphical perspective. Now, if we go back to our slideshow here, and I make it full strength, okay, and I go back to our work, we can see that when we took f and plugged in g, we got x. And if you take g and plug in f and get x, that proves that these functions are indeed inverses of each other. So if you are asked to prove algebraically that functions are inverses of each other, this is what you do. Okay, so to bring this all home, in the third example, I will try to tie up some of the loose ends. So without further ado, let's look at our third and final example and see if we can tie it all together. Okay, so in our final example here, let's look at this. Find the inverse function of f of x equals square root of x minus 4, okay? So now we have to find the inverse function from scratch, and then we're going to verify it both algebraically and graphically. So the first thing I will do is this. F of x is a nickname for y. So instead of f of x, we can just call it y, and that's equal to the square root of x minus 4. Now keep in mind, the domain and range, or the x and y, are completely flipped or reversed on inverse pairs of functions. So the technique to find the inverse is as follows. You take y and you replace it with x, and then you take x and replace it with y, and you leave everything else the same. So again, y became x and x became y. Now, you need to get y by itself, okay? So you need to get y by itself. So you need to think from an algebra perspective, what is going on here? So y is trapped inside of the square root. So that's the first thing you need to do, is get it out of the square root. So to do that, you have to square both sides of the equation. So now you have x squared is equal to, remember, when you square a square root, the symbol goes away. So we're left with just plain y minus 4. So now y is almost by itself, but we have to get rid of the minus 4. So plus 4 to both sides. So we have x squared plus 4 is equal to y. So what we have found here is we have found the inverse of f of x. So the way that you write that is as follows. You write f with this -1 exponent looking thing. That is the nomenclature for an inverse. So this is f inverse of x. It's the inverse function of f of x, and it is equal to x squared plus 4. Okay? So now we have not only the original f of x, which is this guy, square root of x minus 4, we have its inverse function, which is x squared plus 4. So let's remember that, okay? F of x is square root of x minus 4, and the inverse function is x squared plus 4. So let's pop this into Desmos and see what it looks like from a graphical perspective. Okay, so here we are on Desmos, and in red you can see I have f of x equals the square root of x minus 4. You can see this is the graph of the square root function. Due to the minus 4 inside the square root symbol, it's shifted to the right. So this graph doesn't begin until 4 comma 0. So that means the domain is from 4 until infinity, okay, or x is greater than or equal to 4. So now if I flip on the inverse function, which I called it g of x just for ease of use in Desmos, but that is the inverse of f that we just found. If I flip that on, we see a parabola in purple, but they don't look like mirror images. So here's why. So as I just said, the domain of this red square root function, it doesn't start until 4 comma 0. So that means that if we flip that around, that again, when you're looking at domain, you're thinking about the x coordinates, okay? So again, let me try to explain this a little bit more clearly, get out my pen. So the domain doesn't start until 4, so that's your x value, right? At 4 comma 0. So remember, for an inverse function, you switch the coordinates. So then that means that on the inverse, it's not going to start until 0 comma 4, which is right here, okay? And since the domain uses your x coordinate, we're going to have to restrict the domain to x is greater than or equal to 0. So watch what happens if I do that. So I'm going to go over to my equation here of x squared plus 4, and I'm going to put in a space. And you can restrict the domain in Desmos by putting it in a brace. So I have to hit like shift bracket, which is a brace. And I'm going to tell it just to look at or consider x is greater than or equal to 0. And bam, look what happens. It gets rid of the negative portion of this parabola. And now we have our mirror imaging. So if you let me clean this up just a little bit, we have the square root function starts at 4 comma 0, and flip that around. The x squared plus 4 function starts at 0 comma 4, okay? Let me pick another point for you. Here's a point on the red curve, okay, 8 comma 2. So guess what we're going to have on the purple curve? We're going to have 2 comma 8, right? So every point here is, every coordinate is reversed. So for example, if I found like this one, if this was 10 comma 2.449, we would have 2.449 comma 10. Okay, so every x and y is completely reversed from each graph. So to do this professionally, if f of x is the square root of x minus 4, then its inverse is x squared plus 4, with the domain restricted, x is greater than or equal to 0. So that is a graphical approach. We can also put in the y equals x identity function, which is your mirror line, and you can see that you have great symmetry on both sides of the black line. And if you folded it over like a paper airplane, the purple and red graphs would match up perfectly, which is terrific, and that's exactly the idea of inverse functions. Okay, so now we will go back to the previous slide, and we'll figure out how to confirm that these are inverse functions from an analytical algebraic perspective. Okay, so here we have our recap. We have f of x equals the square root of x minus 4. We found previously that the inverse function of that is x squared plus 4. And now we confirmed on Desmos we need a domain restriction that's only true with x is greater than or equal to 0. So now, how can we confirm this algebraically? Well, we will do the following. Again, looking for that identity function. We will say that if we take f and plug in its inverse, we have to get out x, okay? And then if we swap that around and we do the inverse, plug in f of x, we also have to get out x, okay? So let's try it. Since f here is the outer function, I'm just going to write down the f of x, which is the square root of x minus 4. Okay, then I'm going to recopy it. Instead of x, I do my shell. And now we are plugging in the inverse function, plugging in the inverse. Okay, and the inverse function was x squared plus 4, so that goes in. Okay, so now we have the square root of x squared plus 4 minus 4, plus 4 minus 4 cancel out, so we're just left with x squared. And then finally, the square root of x squared is just x. Okay, so that's what we were looking for. That's what you want to see if you're proving that a function has, if you're trying to prove that one function and another function are inverses of each other, you do this composition of functions, f of f inverse. And if you get out x, that is confirmatory. And now we have to do the other way. So now our outer function here is the inverse, the f inverse function. So the f inverse function was x squared plus 4. So that's x squared plus 4. So now I'm going to do my shell. Instead of x, I do parentheses, squared plus 4. And now let's pay attention to what are we plugging in. The inner function is f of x. The f of x was square root of x minus 4. So we've got square root of x minus 4. So the square root of x minus 4 quantity squared, remember the squared power undoes the square root. So we have just x minus 4. Carry down our plus 4. So x minus 4 plus 4, the minus 4 plus 4 zero out. So we have just x. So if you do the composition of f and its inverse, or the inverse plug in f, and you get x both ways, that is algebraic confirmation that you have found inverse functions, a pair of inverse functions. So I've shown you that. I've shown you how to do composition of functions, and I've shown you what it ought to look like on Desmos. So hopefully that is a little good head start for you fine people out there in YouTube land. So I hope that helps and you enjoyed this video. I apologize for the little slide error on the first example, but quite frankly, I'm tired and I don't feel like editing it, so it is what it is. So I hope you all have a good day and good luck with your studies and keep on trucking.